Hello, this is the first video tutorial from Plano West Robotics. Today we'll be talking about the PID controller. PID is a method used in order to achieve accurate and smooth movements. It's used not only in FTC, but also all around the industry. First, let's look at the proportional term. Say we have a circle which represents the target position and a square which represents the system's current position. We can calculate the error between these two positions in order to apply a correction for it. The proportional term applies a correction which is directly proportional to the error, giving us this equation. I'll get into what Kp is later on. While a simple P controller may be enough for some cases, it's usually not ideal. Let's consider this graph of the error over time when only a proportional correction is applied. As you can see, the system will oscillate wildly around the target position. In addition, instead of actually bringing the error down to zero, the error instead converges on a value slightly under the target position. The value that it converges to is known as the steady state error. To combat this steady state error, we can use the integral term. An integral is a way to find the area under the curve of a graph. In a PID controller, the integral is used to bring the area under the graph down to zero, effectively eliminating steady state error. To approximate an integral quickly, we can create rectangles under the curve, whose area is the value at a certain point in time multiplied by some interval dt. Then, the integral can be approximated by adding up all of the areas of these rectangles. For larger values of dt, the approximation is not great. There's a lot of empty space not covered and a lot of extra space where there shouldn't be. To fix this, we can decrease the interval dt. For smaller and smaller values of dt, the approximation of the integral becomes better and better. From this, we can derive this part of the equation. The I term of a PID controller is Ki multiplied by the integral of the error from 0 to the current time. By calculating this integral and applying it to our correction, our steady state error is brought down to 0. However, notice that even though our steady state error is 0, the controller still oscillates wildly around the target. To remove these oscillations, we can make use of the derivative term of the PID controller. The derivative term effectively dampens our output, preventing oscillations. The derivative is the rate of change of a graph. If you remember your Algebra 1 class, to find the rate of change, or slope, you can solve for the change in y over the change in x. In calculus terms, this is known as putting a small change in error over a small change in time, dE over dt. And just like the integral term, for smaller and smaller values of dt, this becomes a better and better approximation. From this, we can derive that the derivative term of the controller is kd multiplied by the derivative of the error over time. By applying the derivative term to our correction, the derivative term will create a dampening effect, removing oscillations from our error. So, from these three parts, we have arrived at our final equation and the following code. But what are Kp, Ki, and Kd? These three values are known as PID coefficients, and they determine how much effect each term has on the output. For example, maybe your proportional term already has a low steady state error, so you don't need a lot of integral correction. Or maybe you notice that your system doesn't oscillate that much when not using a derivative term, so you can get away without having the derivative's dampening effect. Changing these values is what it means to tune a PID controller, and tuning the controller allows you to modify the PID controller's behavior to fit your system. By calculating your controller's output using this equation, you can ensure that your system can smoothly and accurately correct for any error. This is what makes a PID controller extremely useful, not just in FTC, but in the industry as a whole.